Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I think we'll start. We're very pleased to have Walid today with us. Walid's doing his PhD from Berkeley, where he started out in the EE department, and he's been sort of doing more machine learning and optimization related things of late, and his work sort of touches upon many areas of interest in our lab, including game theory and optimization. So we're very interested in hearing what Walid has to tell us.
Thank you, Alec. And thank you all for the invitation. It's a true pleasure to be here. OK, so today I'm going to talk about some of my work on online learning and optimization from continuous to discrete time. So this talk will be, the general topic is how can you design dynamics in continuous time and then discretize them to get algorithms, right? And both for online learning and optimization. OK, so let me say a couple of words of first why we want to study online learning and optimization. Of course, online learning is, so it's the study or designing algorithms for solving sequential decision problems, and these are everywhere. So here I'm just citing a couple of examples, but there are many more than that. So one example that's particularly close to my PhD work is actually inspired from transportation. So my main advisor is Alex Bayan, and he's interested in transportation problems, so both modeling and control of, for example, routing or highway traffic and so on. So in transportation, typically you can route people, and you have information that's arriving in a sequential way, so you can model this as a sequential decision problem. So same thing for routing on the internet, actually. So it's at a much larger scale. And so we have the same types of problems in power networks, for example, although I haven't worked personally on this. And of course, sequential decision problems are also in, let's say, pricing and bidding and online advertising and so on. All right. So one particular aspect also that I want to say about these problems is that in many large-scale systems, it's impractical to solve this in a centralized way, or even impossible. So think of routing on the internet. So it's unreasonable to assume that a particular node has access to the entire state of the network, for example, right? So we have to also think about distributed learning, so online learning that's done in a distributed way. OK, so the second part of the title is convex optimization. And of course, I don't have to convince you that convex optimization is useful in many application areas, so in particular in data-driven decision problems. And so recently, the size of the data has become so large that it's impractical to apply second-order methods. And so this is why there has been an active research on, in particular, on first-order methods, accelerated methods, stochastic methods, and so on, right? And so one particular idea that's been emerging in the last few years, and that I will talk about today, is that some algorithms can be thought of as discretization of a continuous time process, right? And so first, why would you care about doing things in continuous time, or why would you care about this connection? So one reason is that usually in continuous time, the analysis is much simpler, right? So you can study the system and prove its properties, for example, in a much neater and much more elegant way. And then once you have the property on the continuous system, you can try to prove it again on the discrete system, right? And the second reason is that usually it also provides insights on the discrete process. So for example, it can explain why things work. And hopefully, it also streamlines the design of new methods. So once you have an understanding of, for example, why a method works in continuous time, you can generalize that process and come up with new algorithms, for example. So with new dynamics in continuous time, and then after you discretize them, you'll get new algorithms. OK, so really, we need to understand this connection between what happens in continuous time and then what happens after you discretize.
So, well,
all right. Yeah.
Is there a fourth reason?
Yeah.
So I guess often you kind of discretize things because that's what your computer's
Yeah.
digital, right?
Yeah.
But the real world is often much more continuous.
That's also true,
And
yeah.
It seems like an algorithm which starts as continuous, it's discretized to discrete, and then it gives you a natural pathway back towards continuous.
Yeah.
If you want to use that in the future.
That's a very good point, yeah. So as you mentioned, many systems, especially physical systems, are inherently continuous. I mean, they should be modeled as continuous time systems, and then that description is more natural. So in some other problems, I mean, it's maybe it's inherently discrete, but even in those cases, thinking of them as continuous systems and then discretizing can still be helpful. But yeah, you make a very good point. OK. So let's dive right into it. So it's a fairly simple organization of the talk. So the first part, I will talk about this phenomenon, this connection between continuous and discrete for online learning. So in particular, I will talk about the replicator ODE. So it's an ODE that comes up in game theory, and then how to discretize it. In the second part, I will talk about optimization and on a family of ODEs called accelerated mirror descent. So how to get them, and then how to discretize them and show some simulation. And then the last part, I will talk about some ideas for future work. Okay. And so don't hesitate to interrupt me at any point. It's good to make this interactive. Cool. So let's talk about the replicator ODE. So first, a quick word about online learning in games. OK, so here I have, I hope you can read this. The resolution isn't great. But so here I have a fairly simplistic description of an online learning model. So this is probably the simplest thing you can write. So it's played iteratively. As time advances, you play some action, let's say, from some probability distribution xt. So if you're player k, and then you discover some loss function at time t, and then you incur the loss that corresponds to the action that you played, and then you update your distribution. Okay, so this is the model that I will assume for online learning. Okay, and here's one picture of it. So we can think of this as an agent or a player k that's interacting with an environment. So at each step, it plays some action, then it gets some feedback from the environment that's in the form of this outcome or this loss vector, and then it updates its probability distribution. So this distribution, describes what the probability of playing an action is at the next step. Okay, so it updates that. Yeah.
What's k indexing?
So k is indexing players.
Okay.
So I have multiple players, right? So here I'm looking at this problem from the perspective of one player. But of course, if you have a game that has many players, they are coupled, and the other players, we can think of them as part of the environment. And the coupling between these problems is through the loss function, because the loss of one player will depend, of course, on the decisions of others. Okay. And so now, if we think of this in terms of games, we can, of course, describe the equilibria of the game, and they usually provide a good description of the efficiency of the system at steady state. So it tells you what happens once everyone is at a state, so at an equilibrium where they don't need to move anymore, right? However, many real systems rarely operate at equilibrium. So beyond describing the equilibria, you need to also understand the dynamics that get you there, right? And so the dynamics are important to study for two reasons, probably among others. But first, we can think of them as a prescriptive model. So given a problem, you can define a dynamics that will get you to the solution or get you to an equilibrium, but also as a descriptive model. So think of systems with human decision makers. So maybe human players, and they are making sequential decisions, and you want to model how they actually get to the equilibrium, right? So this is kind of the dual role of online learning in games. Okay. And so for this talk, my goal will be to try to define classes of algorithms for which we can prove convergence. Okay? So what I mean by this is that we should come up with a class of algorithms such that if every player uses an algorithm in this class, then the coupled system will converge to equilibrium. Okay? And then there are many related questions that are kind of peripheral to this. So once you prove convergence, you can ask, is it robust to stochastic perturbations? So for example, if I don't observe the true loss vector, but some noisy version of it or maybe some bandit version of it, so I only observe one entry. Also, so built in this problem is the notion of heterogeneous learning. It's the fact that different players can apply different algorithms, so they are not necessarily all doing the same thing. And also, in some cases, you can ask what's the convergence rate. OK. So there's a lot of literature on this. This is a very small sample, but this is just to say that it's an old question. So it dates back to the work of Hanan and Blackwell, and maybe even before then. Hanan studied this in the context of games, and he defined the notion of Hanan consistency. And of course, there are many results. So for some classes of games, for some classes of algorithms, you can prove convergence. Okay. And so actually, there's also a lot of work for this in continuous time. So now you can model the behavior of players. So if I go back to the previous slide, so instead of having a discrete algorithm, you can describe this using an ODE. Right? And this is studied, for example, in what's called evolution in populations. And one particular example is this replicator dynamics that I will talk about in more detail. OK. And so just to have one specific example of a game in mind, so let me give this example. So it's called the routing game. Maybe some of you are familiar with this, but let me review it. So here I copied the online learning model from before. So the routing game is played on a graph. So that represents, let's say, a transportation network, right? And then we have different players. Each has some origin and some destination. So here they are color-coded. For example, I have a first player that wants to go from 0 to 1. And every player, so the possible actions is which path I can take. Okay, so this player has, let's say, can go through this path or this one or this one. And then we have a second player here. Okay, and so the losses then of the players are, of course, determined by the actions of everyone. So I don't give the formal description here, but the intuition is that if there's an edge on this graph that is used by more players, then that edge will be congested, and that will increase the cost on that edge. So that's how the coupling happens, okay, between the players. Okay, so that's a routing game. And now what is online learning on this game? So here I have a picture of a small cartoon that kind of illustrates this. So at iteration t, I have some probability distribution of actions. So I want to pick between different routes. So I sample a path, and then I drive, let's say, to work. And then the assumption is that once I get there, I actually discover the full loss vector. So I know the losses of the alternative paths. So maybe I can do this by talking to my colleagues, or maybe going online and looking at the state of traffic this morning. OK, and then at the end of the iteration, I update my probability distribution. OK, so that's the model. All right. And the main problem, again, is we want to define a class of algorithms such that if everyone uses an algorithm in this class, we have convergence. OK, so convergence to what? To the set of Nash equilibria of this game. So let me say a quick word about what Nash equilibria are in this case. So one way to write it is this equation here, where L is the loss vector, X is the decision of all the players, and X star is an equilibrium. OK, we don't have to go through the details, but if you look at this, you might, this might look familiar. So this actually corresponds to the first order optimality conditions of some convex function. So if this L here function is the gradient of a convex function, then this is exactly the optimality conditions. Okay, so it turns out that that such a function exists, and so this game is called a convex potential game. And so now, X star is a Nash equilibrium if and only if X star is a minimizer of this convex function f, right? So we can think of dynamics of players converging to equilibrium as a minimization of this potential function. So it kind of simplifies the analysis in that sense. Okay, so this is just an illustration of what the optimality condition is. So this is the gradient, and this is any displacement vector from X star to X. Okay, yeah.
Do you need additional conditions for there to exist a convex potential function? Did I miss them?
Yeah, so I didn't detail what the conditions are on this game, but for example, the edge costs on the costs on these edges have to be increasing. So that's.
Oh, you meant this specific routing.
Yeah, for this specific routing game. Yeah. And so what I will say applies to any convex potential game, but yeah, but not for general games. Yeah. Yes.
So can you go back?
Yeah.
So is LKT, is that the loss just for that one action, or is it giving the losses for all actions?
It's for all actions of that particular player. Yeah. So you do discover
So
the
loss for that player is then what, the inner product of LKT and XKT?
yeah. So the expected loss would be the inner product. Yeah. Okay. All right. So in this case, I will focus on convex potential games. Yeah.
Before you go on.
Yeah.
So I'm used to, in general sum games,
Mhm.
converge to correlated equilibria,
Yes.
but not Nash equilibria.
Yeah.
Maybe I'm it's the same question as what Sebastian said, but what's special here? Is it just the game that you're choosing, are all the games you're going to be looking at going to be such that you can converge to Nash equilibria?
Yes. So here it's a Nash equilibrium in the sense of the potential game. So so X is a distribution over actions. So, but it's still a Nash equilibrium, so they're not correlated in this case. Yeah. It is, it is a special property of convex potential games. You cannot hope to do this for any finite player game. Yeah. Yeah.
Do you need
Yes.
the loss for every action, or would it just be slower? Couldn't you?
So yeah, you can adapt this if you were just to observe the loss of the action that you actually took. And so the typical way to do it is that you can come up with an estimate, so with a stochastic estimate of the full loss vector, and then you can apply the same reasoning that I showed here. So this is just to simplify. Yeah. Okay. All right. So let me talk about stochastic approximation now. So the idea is to, as I said, to view the learning dynamics as discretization of the ODE, and then we study convergence of the ODE, and then we relate convergence of a discrete algorithm. So once we go back to discrete time. Okay, so first, what ODE? And so the one we decided to study is the so-called replicator equation. And interestingly, you can obtain it by taking the hedge algorithm. So it's given by this simple update rule. And then so it's parameterized by some learning rate or some step size eta. And so if you take the step size to 0, then you end up with this ODE here. So this is saying that the derivative of the probability of taking action A is given by the simple expression. So it's proportional to XA. And it's multiplied by this inner product. So we can think of this as the average loss minus the loss of a particular action. So if an action has higher loss than the average, then you will decrease its probability and vice versa. Okay? Okay, so we can think of this as there is an underlying continuous time, and the discrete algorithm is kind of discretizing this with steps eta. All right. So and this ODE has been studied, and for example, it's known that so from the game theory literature that all its solution trajectories will converge to the stationary points, which happen to be a superset of Nash equilibria. They include other points, but they include in particular all Nash equilibria. So there is hope to show that they actually converge to Nash equilibria in the convex potential case. Okay, so how do we discretize it? There is some work in stochastic approximation theory that tells us, that gives sufficient conditions for the discrete trajectories to be close to the continuous trajectories in a certain sense that I will explain. Okay, and the condition is this. So if you approximate the derivative by this difference here, this difference equation, xt plus 1 minus xt divided by the step size. So here on the right-hand side, I have exactly a copy of of the derivative in the continuous time, and I can add some perturbation term, some stochastic perturbation. So here eta is a step size, u is a sequence of perturbations, and they have to satisfy some technical condition. And so it looks complicated, but it's actually a mild condition. So for example, sufficient condition is that the qth moment of these perturbations is finite, and the etas decay fast enough. Okay. So it's a simple condition to check. And so under this particular discretization scheme, which is very general, we can show that for convex potential games, the discrete sequence will converge to the Nash equilibria almost truly. Okay. And so the way to prove this is, so the intuitive way is to show, as I said, that the discrete trajectories are close to the continuous trajectories in this particular sense. So in the sense that if you start at, for example, x0 at the trajectory. You propagate the continuous solution. You will end up at some point here. But the next discrete point shouldn't be too far. Okay, so it has to be in a ball of radius, let's say, epsilon. And then you continue to do this, and at every step you make, you are within a ball epsilon. Okay, so it's called an asymptotic pseudo-trajectory if, for any epsilon you pick, this eventually happens. So at a large enough time, you will have this property. Okay, and then, so that's the first step. This is general for any, for any ODE, not necessarily for convex potential ODEs. I mean, for convex potential games. And the second step is to use the convexity to show that, combined with this, you will get convergence to Nash equilibria. Okay.
Don't these errors accumulate?
So that's a good point, and that's why we need also this convexity, right? So because all the trajectories will eventually converge to the same point, it's fine as long as you are close to some trajectory. So, okay, so the technical details, are a little bit more involved. So you can show, for example, that any limit point of this asymptotic pseudo trajectory is also a limit point of the continuous trajectories, so of the continuous flow of the ODE. And from there, because we know that all solution trajectories converge to the to the set of Nash equilibria, you prove that any accumulation point or any limit point of the discrete sequence will be a Nash equilibrium. Yeah.
I guess I missed something earlier on.
Okay.
So the discretized dynamic here, is it like a hedge or it's something?
So yeah, that's a very good point. So hedge is obviously one example because that's where we started, right? So we started from hedge and we took the continuous limit. But you get much more general algorithms than this. So any algorithm that you can write in this form will satisfy this property. So actually, it's an interesting exercise to show that hedge satisfies this condition. It's not obvious. So you basically take, you take the hedge update, you take the difference with this update, and you show that the difference, will be vanishing in this sense. I mean, will not be vanishing, but will satisfy this this condition. Okay, but you can do this. All right. Okay, so I'll just quickly mention that this general method, unfortunately, doesn't give you convergence rates, okay, because of its generality, because here you can pick any perturbation sequence. So here, let me just show a quick illustration of what this looks like in practice. I mean, so here I am plotting the continuous solution trajectory of the ODE, and then the discrete hedge algorithm on top of it. Okay. So I don't know if you can see this, but so at every point here, for example, here there are small circles that show the discrete trajectory. So red is discrete and blue is continuous. So from every point, I propagate the ODE forward, at a time that corresponds to this particular step. And so you do end up at a point that's, so in the beginning it's pretty far, but as you move forward, it becomes, the trajectories become really close to each other. Okay, so this is just a quick illustration. Yeah.
So in some sense, there are two things here, right? So one is kind of assertion about a certain structure of discrete time dynamics staying close throughout the trajectory to the corresponding continuous time dynamics, and then essentially utilizing the fact that continuous time dynamics also actually has good properties for convex potential games, right?
Yes, yes.
I'm wondering, so you said what's specific to convex potential games, what's specific to replicator here? So could I take a different continuous time dynamics that also has the right properties and obtain a discrete time like this?
That's a very good question. So my best guess is that if you can show that the continuous time dynamics will converge to some set, let's say an equilibrium set. It doesn't have to be Nash equilibria, but any equilibrium concept. And that set also has nice properties. So for example, here we use that it is convex. Right. So for example, if it's maybe connected, then that's enough. So maybe you don't need convexity. And then if you do this type of discretization, of stochastic discretization, that will guarantee that the trajectories are closed. Then you can prove the same thing.
I see. But that's not formally known.
That's not known, at least not to my knowledge. Yeah. OK. All right, so let me show a quick example. I'll go very quickly on this. So back to the routing game. Here I simulated this so we have two populations. And I ran a simulation with, actually with noisy losses and with two populations. And each population is applying the hedge algorithm with some sequence of learning rates. Okay. So in this case, because we're applying hedge, we can actually, we have an estimate of the convergence rates. Okay. And so here's the output of the algorithm. So on the left here are the probability distributions of both players or both populations, and on the right are the path losses. Okay, and these are the noisy versions. This is one realization. So you can guess that they are converging. So the path losses are converging to the same value. So here there's a path that has a higher value, but if you look here, the probability of that path is 0. Okay, so it doesn't matter. This is still in equilibrium. So we can also evaluate the potential function, which tells you how far you are from equilibrium. This is one realization again, so it's noisy. But if you average, you will see that it does go to 0. So this is the distance to optimum, as evaluated by the potential as a function of time in log-log scale. So it does decay to 0. Okay, at the rate that's predicted by the theory. Okay. All right. So that was the first part. So that was how to do online learning in continuous time and then discretize. So now we're going to do the same thing for convex optimization. And so in particular, I'll talk about accelerated mirror descent, which is a family of methods. OK, so the problem that I'm going to consider now is minimizing a convex function. And I will assume that it is smooth in the sense that its gradient is Lipschitz. Okay? And I have subject to some constraints. Okay, so x has to be in some convex closed set. All right, and so I will focus on first-order methods, which means that at each step I can evaluate either the function or its gradient. And so the methods I will talk about are we can organize them in two families. So the first one is mirror descent and dual averaging. So they are very similar in spirit, and under some conditions they're actually equivalent. And these converge in 1 over k, so where k is the number of steps. And there's the second family of method, which is Nesterov's accelerated methods, and these have higher convergence, okay, a higher convergence rate, so 1 over k squared. And the goal in here will be to have kind of a unified approach to derive these algorithms, and in particular to derive them in continuous time. Using a Lyapunov argument. So we'll see that one interpretation of all these methods is using some sort of Lyapunov function or some sort of Lyapunov argument. And then once we get the ODE in continuous time, I will show how to discretize. Okay? So that's the agenda for the second part. And I will, to arrive there, to get there, I need two ingredients. So the first one is the ODE version of mirror descent, and the second one is the ODE version of Nesterov's method. So let me review these two. OK, so before doing mirror descent, I will talk about the simpler version of it, which is gradient descent. So gradient descent we can think of as a discretization of this simple ODE. So x dot equals the negative gradient. And this you can show that this converges in 1 over t, in the sense that f of xt minus the optimal value, f star, is less than a constant divided by t. And so to prove this, the idea is to use the appropriate Lyapunov function, which in this case is just the Euclidean distance to optimum. Okay, so it's the norm squared of x of t minus x star, where x star is any minimizer of the function. Okay, so now, and this is unconstrained gradient descent. So then what Nemirovsky and Yudin did when they introduced mirror descent is actually they said, why this particular Lyapunov function? So the Euclidean norm seems to be very specific. So why not a general distance function? So they replaced the Euclidean norm with a Bregman divergence. So I mean the actual definition of it doesn't matter, but we can think of it just as a generalized distance function. Okay, So then their approach is to start from some energy function and then design the dynamics to make that a Lyapunov function. So when I say Lyapunov function, I just mean it's a positive function that is decreasing along trajectories of the system. Okay? So when I evaluate it at x of t, then this has to be decreasing in t. All right. And so they designed the dynamics, and the mirror descent ODE looks like this. So you have actually some dual variable z. So this is the other point that they were making. So this here, this energy function is defined, is a function of x. But they say, OK, we can actually define an energy function that depends on a dual variable z. So they introduce another variable. And so the advantage of this is that now you have a coupled system. So you have z dot equals minus gradient, which looks similar to the gradient descent ODE. And then to get the primal variable x, you apply some nonlinear transformation that's given by this gradient of psi star. Okay, and the picture is like this. So this x is your convex feasible set. So it lives in some space E. So this is the dual space E star. And the main, the main updates or the main algorithm happens in the dual space. So you have z that is evolving in the dual space without constraints, in fact. So it's following the negative gradient. And to get the primal trajectory, you just apply this nonlinear transformation. So this gradient of psi star, we can think of it as just a mathematical object that maps the dual space, the unconstrained dual space, to our feasible set. Okay? There's always a way to construct such a function. So given some convex set, I can come up with such an operator. Okay, so that's the picture that we have to keep in mind. Okay, that's the first ingredient. So how do you go from unconstrained gradient descent to constrained mirror descent? Okay, so the second ingredient is actually a recent work of Su, Boyd, and Condes. So this is in NIPS 2014. So they show that Nesterov's method, so Nesterov's accelerated method, can be interpreted as discretization of an ODE. And so this is a second-order ODE, so in the sense that it involved the second derivative of x. Okay, so to contrast with with the other methods that we've seen so far. Okay, and so the way to prove this is once again come up with the appropriate Lyapunov function. So in this case, it looks like this. So we don't have to to interpret this, but it's they come up with a Lyapunov function, and that's what they use to prove convergence. This 1 over t squared rate. Okay. So, however, this only works for the unconstrained version of Nesterov. Okay. So the question is, how can we apply this? How can we extend this once you have constraints? And there we will use this idea from mirror descent. Okay. And now this is what you do. So first, you have to define the appropriate energy function. So here, I'm going to apply sort of an inverse approach. Usually, you start from an algorithm, and then you find the appropriate energy function for it. So now what I'm saying is, which is the same as what Nemirovsky and Yudin did, is start from the appropriate energy function, and then come up with the dynamics to make that decreasing. Okay. So what does the energy function look like in this case? It has two terms. So the first term is this t squared times the distance to optimum as measured by f. And the second term is this Bregman divergence term that we saw from mirror descent. Okay? So one intuitive way to interpret this is that this first term here encodes the convergence rate that you're after, okay? Because you have this t squared times f minus f star. So I'll explain why. And the second term encodes the constraints. Okay, so it's a very natural choice of energy function. And z here, again, is a dual variable. And so now once you come up with the energy function, you can compute its derivative, and then you can choose the z dot and x dot to make the derivative less than 0. Okay? And then you guarantee by construction of the ODE that this is a Lyapunov function. And as an immediate consequence, you get the desired convergence rate. Why? Because by definition of the energy, we can write that f minus f star is less than v divided by t squared, right? Just because this is a positive term. And then because v is decreasing, this is less than its value at 0. But its value at 0, we know exactly what it is. It's so this term disappears, and this is the Bregman divergence at 0, at C0. Okay, so this only depends on the initial condition. And so you get this constant divided by t squared. Okay. Yeah.
You say that second term encodes the constraints. You mean this in a soft constraint sense, or can it actually be?
It's a hard constraint set.
The indicator function of the convex set?
Yeah, exactly. So yeah, it encodes it in a specific way. So it's the choice of psi star that has to be careful. You know, given a convex set, you can always come up with such a function psi. And so I have some details in some backup slides if we have time for that at the end of the talk.
Why isn't R always 2?
Why isn't R always 2? Because so that provides a little bit of flexibility in the choice of algorithm. Right? And then so this defines a family of methods. And actually, we'll see later that the choice.
Define the family of methods as you get worse and worse.
Oh yeah. So actually, yeah, this is an artifact of the analysis. But in fact, it seems that there's, the optimal value of R is not 2. It's not the smallest one. So yeah, there is, I think you can do, a better analysis to prove a better bound than this. This is just, a bound. Yeah, I'll show some simulations that get to this point. Yeah. Okay, so, so we came up with this ODE, and I mean, it's still not very intuitive because, okay, z dot, it's following the negative gradient. That's intuitive enough. It's multiplied by t, though, which means that you're putting more weight on the later gradients. But x dot looks kind of strange. I mean, what is this ODE? So it turns out that you can rewrite it in integral form. So if you integrate this equation, then you can show that this is equivalent to x being the weighted average of this gradient of psi star of z. Okay, so with the appropriate weights. So here they depend on R. So the picture in this case would be something like this. So I apologize again for the quality, but so as a mirror descent, you have this kind of something that happens in the primal space and something in the dual space. So now Z evolves in the dual space, and it follows negative t times the gradient. And in the primal space, you first apply this mirror operator. So you get this, this trajectory here, which is grad psi star applied to z, and then you do averaging on top of that to get x. Okay, so it's a very simple interpretation in this sense, and it kind of formalizes this connection between acceleration and averaging that's been made before in some special cases. Okay, and so the next natural question is, okay, here it's for a particular choice of weighting, but what if why that particular choice? And it turns out that you can do this in a more general way by picking any weighting function w. So if we call capital W its integral, then the only condition that you need is that the ratio has to be bigger than 2 over t. Okay, so this puts some constraint on w. And then you have to adapt, of course, the dynamics. So z dot becomes this. So minus w divided by capital W times t squared. But this increases even further the family of methods. Okay, so let me give a quick example. So here, suppose that the feasible set is the simplex. So we go back to optimizing over probability distributions. So there's kind of a common choice of regularizer. So you can pick psi to be the negative entropy. In that case, you can actually compute psi star and the gradient of psi star in closed form. And you can get everything in closed form, basically. So once you apply this accelerated mirror descent ODE, you get something interesting. So you get an accelerated version of the replicator ODE that we saw in the first part of the talk, right? So so what happens here, it's another variable z tilde. So z tilde is the mirror of z, so it's grad psi star of z. Okay, so z tilde here follows the replicator dynamics. It's exactly what we had before, with the difference that the gradient is evaluated at x, which is this weighted average of z. Okay, so it's replicator plus averaging. You get an accelerated replicator that has faster convergence rate. Okay, so let me now show some numerical examples. So I will show a few of these plots. So let me explain what I'm drawing here. So on the top left, I'll show the value of the function. So here in this example, I'm comparing mirror descent, so the non-accelerated version to the accelerated version. So this is the value of the Lyapunov function. So in particular, in the accelerated mirror descent, it should always be decreasing. So that was by construction. And the bottom plots show the trajectory. So this is the trajectory projected on a plane, and this is the trajectory on the actual function, okay, overlaid on the function. Okay, so let me play this. So this is just to compare the two methods. This is mirror descent, and this is accelerated mirror descent on the simplex. So this example is minimizing quadratic over the simplex, okay, in R3, just to be able to visualize. And so so as you expect, this is faster. And actually, if you so this is in log-log scale. So if you fit this with a line, you will get the 1/k² rate. So the Lyapunov function is decreasing for the accelerated version. It's not for the original mirror descent, as expected. And so another qualitative difference is that for the accelerated version, we see these oscillations, right? So it does get faster to optimum, but it oscillates a lot around optimum, right? And then, so we'll see actually some interpretation of why this happens. Okay, so that was a first example. And so this is the interpretation. So another way to write this system of ODEs, so we had z and x before. So now you can eliminate the z variable, and you can write everything in terms of x. So it looks more complicated, but so in particular, it involves all these nonlinear terms that depend on psi. So, but at least conceptually, it's similar enough to a physical system. So here you have an x double dot term, which is an acceleration. So let's ignore this term for now. Let's ignore this term, right? So if I had just x double dot equals the negative gradient of f, then this would be a nonlinear oscillator. Okay, so I have some potential f, and I have a particle in that potential, and its acceleration is given by the negative gradient of the potential. Okay, so of course such a system will never converge because it's a conservative system, right? So the energy would be conserved, then you would just oscillate in this potential. So that's why we have this second term here, the x dot term, which we can think of as a dissipation term. So it's kind of a friction term, so it's proportional to x dot. And the role of that term is to dissipate energy so that you will get eventually to the bottom of this potential. Now this term is more complicated to understand, so I don't have a clear understanding of it. I mean, in this form at least, but it encodes the constraints. Okay, so you want somehow to change the gradient of f such that as you're getting close to the boundary or to the relative boundary of the set, you are pushed away from it, right? So because you want to stay in the feasible set. Okay, so that's kind of another interpretation. So a special case is if you are in the unconstrained case, then this term disappears. It becomes the identity. And this term, as I said, we can think of as a vanishing friction term. Okay, so let me show you quickly what happens if I replace this by a constant here. So instead of r divided by t, I just have a constant. So it's a constant friction term. And then I vary that constant. So in the beginning here, that constant is pretty high, and then or the alpha is pretty low. So this is r divided by alpha. And then as I increase, this is the initial trajectory, so it gets to the minimizer pretty fast. And then as I increase the constant, we see these oscillations occur. Okay, and so which corresponds to what we see in the accelerated version of mirror descent, right? And it's intuitive enough. If you're dissipating less energy, then you will oscillate more. Okay. And so here's another example that, so I chose it in such a way that you will hit the boundary at some point. And this illustrates kind of the effect of this term here. So as you're approaching the boundary, you kind of, you bounce back and you oscillate now in the opposite direction. Okay. And so this is for constant friction. Now if we apply the same thing, the same simulation, but now I'm keeping the 1/t, but varying r, the r parameter. And this goes back to your question, John. So as you vary r, so here I start with r equals 2, and then I increase it up to r equals 50. So in the beginning, I start with a lot of oscillation. So let me run it again. OK. And then as r increases, we get there faster. But if you increase r too much, actually you will be too slow. right? So you're dissipating too much energy, so it takes you a very long time to get there. So, you know, I don't think there's an optimal value of R per se, but given a particular horizon, you can, you know, choose. I mean, there seems to be an optimal value of R given a horizon. Yeah, Alec.
So another interesting qualitative difference that I see is, right, so gradient descent, at least in the unconstrained case, is a guaranteed descent algorithm monotonically, which at least Nestrov's accelerated gradient is not.
Doesn't guarantee.
It does increase the function value, and definitely your variant seems to have the same property in this case.
Yeah.
What I found interesting was at least as you were changing the values of R, it
at
did
some point,
start to. Do you have any understanding of this?
So I think, I mean, a naive answer is probably from physics. So we know the kind of the typical oscillators. So for example, a pendulum. So if you add a friction term, then there's always a critical damping. So there's kind of underdamped, overdamped, and critically damped. So I think what you want is that your system is critically damped, because you won't get these oscillations, so you guarantee that the function value is decreasing. But at the same time, if you overdamp, then it will be slower. So this is a more complicated system, and you know, understanding what's the optimal value of R is harder in that case. But an interesting question would be, can we actually adaptively change R? Right? So not have it be a constant here, but actually a function of maybe of time, or you know, a function of the gradient of f or something like that, so that you can adapt R on the fly. Yeah, the analysis of that might be very hard, but at least come up with some heuristics of how to choose R. Okay. All right. So I realize that we're running out of time, so I'll try to go a little bit faster. Okay. So another question of theoretical interest is to show that this ODE system actually has a solution, because you know, it's very nice. We've proved that you know, if a solution exists, then it will have the right convergence rate. But of course, this is meaningless if there is no solution. And so there is a little bit of a challenge there, because okay, so the first idea you have, if you want to prove that there exists a solution, is you want to apply something like the Cauchy-Lipschitz theorem. And that requires that the right-hand side is Lipschitz, okay, that these are Lipschitz functions for any finite value of t. Okay, this is fine. It's Lipschitz. So even though, you know, so if I fix t, if I fix an upper bound on t, this is Lipschitz. But this here blows up at t equals 0. Okay, so there's a problem there. And the way around it is to define a family of, you know, quote unquote smoothed ODEs by replacing t by the maximum of t and delta, and then show that for any such smoothed ODE there exists a solution, and then you can extract a converging subsequence of these solutions that will go to a solution of the original ODE. Okay, that shows existence, and uniqueness is yet another argument. Okay, so at least we know that in continuous time things are nice, and we have these interpretations. So now going back to the discrete time, how do we discretize such a system, actually? So the first thing you can try is, for example, apply an Euler discretization scheme. And what that means is just replace z dot by this difference quotient, right? So zk plus 1 minus zk divided by root s, and same thing with x dot. Okay, and the way to prove that this has the same convergence rate, so you'd like to show that this also converges in 1 over k squared, is to use the same Lyapunov function. Unfortunately, that doesn't quite work in this form, so you have to change it slightly. So this is the final version of the algorithm. So in the end, what you do is, so you have these two variables, so z and x. And here I'm writing it in terms of z tilde, which is the mirror of z, so the gradient of psi star applied to z. So zk plus 1, or z tilde k plus 1, is the minimizer of this function, and this is a mirror descent step, but with increasing step size. Okay, so the step size is here kr over s. S is some parameter, and so I increase that by s. And the second update is x tilde here, is I minimize, it's the same thing, except with a constant step size. Okay, and you can use also two different regularizers here. And then, so once you perform these two updates, you do a convex combination with a particular choice of lambda. So this convex combination step corresponds to the averaging step in continuous time. Okay, if you think about it, so the next step when you're doing averaging can be thought of as a convex combination of the previous average and the new point that you added. Okay. Okay, and so this is the picture in discrete time. So same thing, we have a dual variable that's following negative k times the gradient, and in the primal space you do these two steps and then a convex combination of the two. Okay. And so with this slight modification, you can prove the same convergence rate in the sense that f of this x tilde, so of the green update, minus f star is less than some constant divided by k squared. Okay. And so the proof here actually uses the same Lyapunov function from continuous time. But we had to make that small change to make things work. Okay, so let me say a quick word about restarting now. So because of these oscillations that we've seen, you can think, once you start oscillating, it means that at some point you're going in a bad direction, right? So for example, if you think of this particle moving through the potential, if you're not damping it enough, then at some point it's going up this potential again, right? So if you can detect that and then somehow restart the algorithm by stopping that particle and then dropping it again in the potential, then it should get to the optimum faster, right? And this is what the restarting does. So you have some restart condition that you check for, and then if that's true, then basically you reset time to 0, and then you have to also reinitialize the dual variable at a point that matches the current primal variable. Okay. And so one possible restarting condition is you look at the gradient. So if the update xk plus 1 minus xk points in the same direction as the gradient, then that's bad because you're increasing the function value, right? So another one is a speed restart. So if your speed decreases, it probably means that you're going up the function value again. Okay. So these are the two that I will compare here. So this is the same plot on the same function. Now I'm comparing mirror descent in blue. So accelerated mirror descent in green. Red is restarting with the speed restart, and the cyan is with the gradient restart. Okay. So it does look like restarting in practice improves convergence. So although here the speed restarting is a little bit more conservative, so it restarts more often, but it's so it's slower in the beginning, but eventually it will beat the non-restarted version. Okay. And so if I run it one more time, so for example here at this point you see that it decided to restart and move in the right direction, whereas the non-restarted version will keep oscillating, right? So you do eliminate quite a bit of oscillation that way. Okay, so unfortunately we don't have any theoretical guarantees on how much restarting saves you, but in practice it seems to work really well. All right. Okay. So another interesting thing is to observe is that actually the Lyapunov function with the restart isn't monotonically decreasing anymore. So that's not the right argument to use anymore. So you have to come up with another analysis. Okay. So I'll skip this. This is just another example, but with a weakly convex function. So the only difference is that now, okay, it only takes a few seconds, so I'll show it. So now you have a set of solutions. So you don't have a single minimizer anymore. So instead of all the algorithms converging to one point, different algorithms will converge to different points. But it's interesting that you do converge to some point in the feasible set, because all the theory tells you is that f will go to f star. But you might have situations where you get arbitrarily close to the solution set, but you still oscillate around it. But this is not what happens in practice. And actually, that's another interesting question to investigate theoretically. Can we prove that there is always convergence to some point in the optimizers?
But your step sizes are going to 0. I mean, if your gradients are bounded and step sizes are going to 0, how could you continue oscillating?
So in this case, it's a little bit more delicate because in the dual space, at least, the step sizes are t times the gradient. But you could argue that the gradient maybe goes at a rate of 1 over t squared, the norm of the gradient. You know, it's, yeah.
Okay.
Yeah. So I do believe that it's possible to do it, to prove this convergence, but it will take a little bit of work. OK. So now let me conclude with very briefly some words on future directions. So, OK, one thing that I did not talk about today is estimation of player dynamics. So I told you at some point in the talk that I like to think of online learning both in its role as a prescriptive model, so when you have a sequential decision problem that you want to solve, but also as a descriptive model that tells you how players would behave or how they would arrive at equilibrium. And so we tried to play around with this idea a little bit. So imagine now you have a system with human decision makers, and you get to observe their decisions. Can you fit a model of online learning to these observations? Okay, so here I'm observing distributions, so their probability distribution. So here I'm cheating a little bit by telling players to input distribution instead of pick a single action. But you could do this if you had a large number of players, then you can get some estimate of distributions. Okay, and so we tried this with the routing game. So we implemented an interface for the routing game, and we used it to collect these observations, and then try to fit this online learning model. And so we have some preliminary result. This is what the interface looks like. So once you log in, you have a picture of the graph. You have your origin and your destination, and you have this interface to pick your distribution. So you put weights on different paths. Okay, and then you have some feedback. So we tell you what the losses are on different paths and what your history of decisions were and things like that. Okay, so that's the interface. And so I think, so from this preliminary run of the experiment, we do see interesting things. For example, that players do converge to Nash equilibrium even though they don't coordinate. So everyone just gets the feedback on their own losses. So, okay, convergence here is a big word, but they get close to equilibrium, right? So you can't talk about convergence in finite time, right? And so there are some theoretical questions that are interesting there. So for example, can you provide some statistical guarantees if you assume that they do follow some learning dynamics with maybe some distribution on the parameters? Can you recover that given these observations? Another one is, so once you have this estimate of their dynamics, can you do optimal control on top of it? So you can think of actuating the system, for example, in the routing game by imposing tolls on different edges of the network, right? And so I think another fun thing to do would be to extend this web application. So here it's specific to the routing game, but actually there are many, I mean, it took a while to actually have a robust system. So because we had to think of what happens when a player drops out of the game, for example, loses connection and things like that. So I think we can reuse the infrastructure. So it's a very complex infrastructure to come up with other examples of games. Okay. So now another question I think of practical interest is, so I talked about this mirror operator, so this gradient of psi star. And this is actually a basic component in many algorithms, both for optimization and online learning, right? So you have some feasible set X, some dual vector Z, and you want to solve this problem. So the gradient of psi star, you can write it as the maximizer of some linear function plus or minus a regularizer. Okay. So this here, I mean, many algorithms rely on this, so they do such an update at every step. So having an efficient computation of this is very important. So the question is, which choices of regularizer psi lead to a simple expression of this? And there are some special cases. For example, in the case of simplex, as I said, when you take the negative entropy, you have a closed form actually for this. But you can also do it efficiently for quadratics and more generally for any F divergence. Right? There are other special cases. For example, in the non-negative orthon, there are some known choices of psi or some kind of typical choices of psi. But the question is, can we do this more generally, let's say for polytopes? Can we do it for special classes of convex sets? Maybe sub-level sets of quadratics or things like this, right? Or maybe is there even a universal choice of psi for which, in some sense, for which gradient of psi star is simple? Okay, so then the next question, which is related to learning in games, is how can we do online learning when the action set is infinite? Okay, so here I'm writing again the online learning problem, except here, so instead of picking a probability distribution over a finite number of actions, I'm picking a distribution over a general set S. Okay, and so after you pick this distribution, you are revealed the loss function, which is now a function that goes from S to some bounded interval. And then I incur some expected loss, which in this case is an integral. Okay, so it's an integral over the set of the probability or of the density x of that action times the loss evaluated at that action. Okay, so I can also define the regret, in exactly the same way as in the finite case, except now the inner products are integrals. So this has obvious applications to learning in games because we can think of games in which the action set is infinite, so it's not a finite set. And also we can apply this to other decision problems, not necessarily in games, but other decision problems on any set. So in particular, I'm interested in the non-convex case because if the set is convex and the loss function is convex, then this is the special case of online convex optimization, and there's a lot of work on this already. Very interesting work. So there is less work in the case where S is not convex, and also when the function, so I guess when the function is Lipschitz, there is work. But when S is not convex, there isn't work. So we started looking at this. And so it turns out that it suffices that S is only locally convex. So you don't need this global property. So in particular, if S, so locally convex means that at any point, there is a convex subset that contains that point. Okay, so it's just a local property. Okay, so in that case, you can also come up with no regret algorithms. But assuming that you observe the full function. Okay, so a question is, can you extend this to the banded feedback case? So instead of observing the full function at each step, you only observe its value at the point you played or at the action you played. So you sample some action from your distribution, and then you observe the value of the function at that point, which is a more, I think, realistic assumption, because especially in the case of games, you don't, maybe you don't observe the full loss function, except maybe in some very special cases, like in matrix games and so on, where you know the matrix a priori. Okay, and the final topic that I'm very excited about is this dynamical systems approach to optimization. So as I said, it's a fairly recent topic, and I think there's a lot to be done. So the vision behind it is that instead of thinking of the problem purely in discrete terms, you can do the design in continuous time. And the reason is because it's simpler, because it can give you some intuition. So we've seen some interpretations of, for example, of the acceleration. And then, so what's missing, I think, right now is how can you do the discretization in kind of a principled and streamlined way? Because right now it still seems to be kind of an ad hoc process where you come up with an ODE, then you have to be very careful in discretizing it. Okay, and so for practitioners, maybe they don't need to necessarily worry about this. So as a first cut, you can maybe do the design in continuous time and then feed it to an off-the-shelf numerical solver, okay, for that ODE. And then you just have to think of the problem in terms of continuous time. Okay, and so there's still a lot to do to develop the theory. For example, in what I showed, study the effect of R. So as I said, maybe even come up with an adaptive heuristic for choosing R, so that R parameter, the damping. Also study restarting heuristics and show guarantees. So show that you can guarantee that it speeds up the convergence. Also generalize this to monotone operators. I think this is pretty exciting. So I've seen some work in actually in continuous time ODEs that handle monotone operators. So not necessarily convex functions, but so convex optimization is a special case because the gradient of a convex function is a monotone operator, but we can potentially do this more generally. Another generalization is composite optimization. So here I'm assuming that f is smooth, but what if f isn't? Or f is smooth, but you add some non-smooth term. And also to stochastic methods. So right now it's deterministic discretization, but can we do this with stochastic discretizations? Of course, you will have lower rates and so on, but I think it's also important to do this. OK, and that concludes my talk. Thanks. OK, any other questions?
We're already running a little late.
Yeah, yeah. Sorry that this took a little bit longer.